Hi, Bill.
Oh, okay, that's better.
Good morning.
Good morning.
Good morning, Professor.
Okay, we're all here. That's good.
I'm still getting organized here a bit. Good morning.
Good morning. How are you?
Muy bien, gracias.
Qué bueno, muy bien.
¿Usted?
Bien, bien. Thank you. Yeah.
And Bill? Bill, do you copy?
Yeah, I'm here. No problem.
Sorry?
Yes,
Yeah, Bill.
I'm still getting organized here on my desktop. But I think that should be right. Now, one more thing. That should do it. Okay. Is that going to work? Okay, there we are. Okay, sorry about that. I was just a little disoriented because I updated version of Zoom, and of course it changes something a little bit. but
And I saw now we can see the four screens.
yes.
Okay, that's good.
All right.
Okay.
So I received the updated submission uses that you sent to the conference.
Yeah, I received it also.
Okay, great. And also, Dr. Sopcich, you sent um, a brief outline of the work that you were doing. Um,
Yeah, I sent it yesterday. I didn't have much time, but I sent everything what the tech file and also macros and so on.
mhm.
Also, a very interesting AI. I think AI is very interesting as well.
Yeah, it can be useful, but I think it also can be a bit misleading at times. You know, it's
For sure. Yeah, hallucinations, just like humans.
yes, that was a comment. Another fellow that I speak to on Zoom quite a bit, mostly about quantum mechanics. We've both been using AI to do, or at least attempt to do, some of the mathematics involved, and we both had the experience that the AI produces a result that looks very convincing. Until you actually like try to write a computer program or something to actually implement what the AI is describing, you realize, well, I mean, it's not much better than a first year, grad student maybe. So that you could, uh, it's maybe the biggest problem is that it tends to be a bit uh, um, what's the right word?
It's very sure of itself.
Yeah, well, and it's also very reassuring to the person who asks the question. Like
That's
it's
true.
very uh,
Accommodating.
yeah, or I was going to say even there's a word that just escapes me right now that means something like uh, almost patronizing, like almost like always saying, oh, that's a brilliant idea, and that let's work on this together, and
Yeah,
very very leading, very very
sure. Remember, we're all training AI as we talk to it. That's the only reason why we have access to it, because it wants us to help train it.
yeah, perhaps. Uh, but I do find too that it has an unexpectedly wide knowledge of things,
Exactly.
so it's like uh, you
Encyclopedia.
can ask some questions and work with it, and you actually do gain something, because it's like talking to someone who is an expert in everything, and or like knowledgeable about everything, but an expert in none of them exactly, like, so it but it
It's getting better all the time, though.
oh yes, absolutely. uh I I can see why people think that it's promising, and but it's like any new tool. It's hard to know how to use it properly, like what to do with it. Um, in the work that I was doing with my friend on quantum mechanics, over the years, we usually exchange computer programs that are expressing, some aspect of models uh, in quantum mechanics. And over the last couple of years, I've become very like not very productive at all. Like it gets harder and harder to write large pieces of code, computer code like that. But then suddenly with AI, AI can generate computer code, based on just a short paragraph. You can say a short paragraph about what you want to do, and then a few minutes later, you have a complete 500 line program that implements something closely related to what you were asking for. But then my experience was that after, that's very rewarding. You think you made a lot of progress, and you can probably, run the program and see what it produces. But since it was the AI that produced the program and not myself sitting in front of it thinking while I wrote the program, the result is not nearly as useful as it looks on the surface.
Well, I have an interesting
You
story I
can
tell.
spend like well, in my case, I spent like 2 weeks looking at this program that was generated and producing results that seemed relevant, only to find in the end that if I asked the question a different way, it could prove that what it was trying to do could never work. I mean, it's like I said in the end, like 2 weeks later, I said, well, this, can this ever work? Is this ever, it looks sort of convincing, but can it ever work? And so I basically went back and said, well, could you show strictly, formally in mathematics that this approach can produce the type of statistics that I was looking for? And within a very short time, it came back with a mathematical analysis that said, no, this can never generate what it is you asked me to do. But 2 weeks ago, it generated a 500-line computer program, which was a sort of convincing attempt to actually implement something, which it could easily have shown in the beginning that it would never be possible. So it felt like, I learned a lot in the end, but I probably would have learned just as much if I had just ignored, AI and sat down and tried to write it myself. I probably would have come to the realization that this approach wasn't going to work a lot sooner.
I had a friend that just told me the other day that he was going to hire his grandson and pay him for a month's work on writing some code. And his grandson says, well, actually, let's get AI to write the code and then we'll fix the code. And it's turned out that AI did write the code that they wanted. It didn't work, but it only took him an hour to fix the code that he was planning on paying his grandson a month's pay to do. So a little more successful story.
Yeah. Well, a lot depends, what you get depends a great deal on exactly how you ask for it.
Well, that's true. That's right. Your prompts are very important.
Yes.
The important tool is how I have to formulate my question, because if you don't formulate your question in a right way, then you are getting nothing useful.
Yeah.
Yes.
Well, the strange thing is that it often looks very useful on the surface. It often is quite convincing initially.
Yes, but maybe wrong. No.
Yes, wrong subtly, somehow or another. Like
yes,
and well, I don't know. Well, I guess it's just one more thing that we have to learn how to use. But probably not as revolutionary as some of the companies that are promoting it would like us to believe, I think.
Well, it is helping a lot. For example, I transferred my website out of they were charging me $90 for every 3 months, and with the help of AI, I was able to transform it or to pull it off that particular server, which was ripping me off, and get it for $16 for 1 year. But they give you the instructions, but you can't read all it. They want to be confusing as possible in order to get as much money out of you. So, but AI helped me get out of that awful situation, which I'd been in for years, keeping my website up. So it's
Yeah,
and they talk more about agents now. They actually want to let AI take control, which is even, it explained to me what I had to do clearly, but very soon it'll be able to do it for me. Anyway, it's powerful. There's no doubt about it. It's hard to say where it's going, though.
yeah, we'll see. But definitely one shouldn't ignore it, I think. One just has to sort of see how it evolves and how it can, what sort of role it can play eventually. Okay, so how should we proceed today? Did you want to review your submission to the conference, Jesus? Is that?
Yeah, I'd like to see. Yeah,
Maybe we can review this, and then because the ideas of Professor Sobczyk about including the viewpoint of duality in the way that he had been presented. And I think that needs to get some place here, but not it is too easy to
not
include.
too much.
Not too much.
No, I think I was interested in trying to understand more closely exactly how it all fits together. I think it will fit together, but it's not all clear in my mind yet. That's why I was trying to get AI to help out too.
I'm going to take my pen in the way that I can write something in the screen.
Yeah, the central notion, I think that that you need that we should focus on, I think, is this relationship between local and global, and I to the extent that I can understand the presentation that you prepared, Jesus. I mean that is one of the central ideas in that paper, but I have trouble seeing the application. Like seeing how the specific representation that Dr. Sobczyk is using, how that maps into the
It fits in.
ideas in the category theory.
Yeah, but maybe we can start with the presentation, and in this way, I think that we can clarify some of these topics.
Okay.
Wait a moment, please.
Okay.
Okay, I'm going to share my screen. Can you see now my screen?
Yes.
Yes, that's good.
Okay, then I am going in the first slide, I think that we don't need to stop. Then I go fast in this, but I like to start here in categorification of Clifford algebras. Okay, then okay, here is the ideas that Professor Garrett presented or sent in his document, but I put away the final conclusion because I think that category theory help to us to understand the geometric ideas included in Clifford algebras. Then I put apart this comment, and only I left in terms of the procedure that we follow in this. Okay, and then we start here with the idea of an universal arrow that permits us going from the from a scalar field. We can build an vector field like a module of the scalar field. And then with this, we can construct a vector field using an universal arrow that permits to us to express this vector field in terms of a basis. Then this idea is important because with this we can speak about the standard definition of Clifford algebras in terms of the vectors of the base of a vector field. Then with this, the Clifford algebra definition requires, after of this, the quadratic form used for that definition. That Clifford expressed in terms of some rules for the product of these based vectors. Okay, then, and this is an important property of this category, then we can find a contravariant functor that sometimes is called the dual functor. The idea is that when we, if we take morphisms from one vector space to the other, then this wielded in the set category. Here it is important to clarify that we have here in the set category, and here we are in the vect F category. Then functor d bar is the required element that permit to us going from the vector space category to the set category, where that is where we build the vector space. And then you can see that here we have a contravariant functor. Then these contravariant functors are inverting the relation that are defined in the vector space category, and in this set category we have the opposite the opposite relation. Okay, then this property can be wielded with an with a bijection that you can see here, this property. Then we can change the role of the vector space W and B. And then you can see how this relation is inverted in this bijection. No? Okay. In this way, it is not so clear how the duality concept is present. But if we write this relation in terms of a bijection wielded in an adjunction, then you can find in a pretty way how these two functors are in this adjunctions, and then we can see that the functor D up is the dual of the functor D. And then with this idea, we can build in an easy way the concept of duality in this category. You can see that we go from, we are using the vector space category and the opposite category of vector space. And with this, then we have the definition of these functors that have the object functor defined in this way, and the arrow functors defined in this another way. Then we have here explicit the relation between the morphemes in the opposite category related with the morphemes in the original category that was defined in terms of the contravariant functor. Then here is how we build this relation from the first one that we presented before. And then you can see that the adjunction now leave the vector space in the same order, and then the functors are going from acting in one vector space to the another vector space. And then in this way, this is the dual functors in the category. Then I think that this is too much important to understand, because the principle of duality in the vector space category is wielded in this way. Okay. Then after of this, we are going to build a subcategory that is the important concept for speak about local and global duality. Because a problem that I found here is, what is the meaning of localized category? Because when we speak about the local duality, first we need to understand what is the meaning of localization here. And then this is an important thing here. And in this way, I started here with the definition of a finite group inside the category that is used for building a representation of this category in terms of this group. This permits to us to understand this representation in terms of modules and a direct sum of modules of these subcategories. Then the concept of locality is wielded in this way. If we can express the vector space in if we can express the algebra in terms of subalgebras, then we can speak about locality, and we can speak about the global properties in the algebra. Then this is important, and in the first attempt to build this category in these terms is using the Grothendieck group. That Grothendieck group wielded these ideas for abelian categories. Then in an abelian category, we can split the category in terms of modules. And in this way, we can relate the global category with the local subcategories. Then, in the case of vector space of multivectors, then this way of splitting the vector space is in terms of modules that, if we start with this representation of the vector space in terms of a base, I am thinking here that the dimension of this space is n, then we can see that a monomial in the in this graded in this in terms of these graded modules can be defined in this way, and these elements are used for define the representation of this algebra in terms of a graded algebra. And then with this idea, we can build a dual representation of this. And this dual representation is built exactly in terms of these monomials. Then we have here the base of the vector space, and here we have the base of the dual of the vector space. Then with this idea, then we can express the global duality, because the global duality is built here with this relation. You can see that here we are not defined yet the Clifford algebra. We are speaking here about of a multi-vector graded algebra. And then in this multi-vector graded algebra, we can build this representation of the vector space in this way. Okay. And then now it's the problem of construction of a graded subalgebra. And then for this, we need a two-sided ideal. Remember that in a module, if I have a module and I have an idempotent in this module, then we can get a submodule applying this idempotent to the module. And another way is using a left and right product in a way that we can build a two-sided ideal in this model. Then the idea is that we can with this get up a projection from the multigrade algebra to the representation of this algebra in terms of this two-sided idea. Okay. Then with this, we can get a subalgebras in these terms. In the case of Clifford algebras, then we can use the vector base, and then with this vector base, we can build a idempotent, and with this idempotent, we can get some subalgebras that are used for the local duality. Okay, then here we start building the Clifford algebra in like sub algebra in the multi-vector space, and then we can see this important process of building, because this is performed with the use of the quadratic form. Then the quadratic form is essential in this building process, and then we can build from the vector space beam a Clifford algebra using the quadratic form. And then after using this quadratic form, there is a correspondence with the multigrade algebra on the vector space that either can be built directly using these morphisms from the vector space to the multigrade algebra. Then this process gives to us the fundamental properties of the Clifford algebra. And then either we can, from the vector space, build a Clifford algebra that is projected inside the multigraded algebra. Okay. A comment here that I have not included in the paper, but I think that it is important, and maybe we need to work for.
I think that looks very good to me. That you are able to talk about global duality versus local duality by what you've just said. It looks like it's. I believe it's true. I think it's very good, actually. It looks good to me. Yeah. So you can use either local duality or global duality, essentially to capture any geometric algebra, and that's where the classification of Clifford algebras becomes very important. If you look at it in terms of local duality or global duality, so you're really talking about, in either case, all Clifford algebras with whatever the signature may be of the quadratic forms, of course, that define them.
Yes, and in fact, in the definition of the quadratic form, we can use any kind of quadratic forms. And the idea is that if we get to relate with, for example, a symmetric bilinear form, then we get the standard representation of Clifford algebras. But we can use different quadratic forms, not even expressible in terms of symmetric bilinear forms, and then we can get some interesting results.
Yeah. There's one other point. Do complex Clifford algebras or Clifford algebras over the complex numbers arise in your discussions that you're talking about now? Where does the idea of a Clifford algebra over the complex numbers become involved. I think that's also important. And as far as the classification of Clifford algebras, it becomes very simple in terms of complex Clifford algebras.
Yes, but here, okay, not in this slide. Yes, here, because we are using algebras over F, where F is whatever scalar field you like.
Could it be a finite field as well? There are finite fields as well, of course. Very arbitrary fields can be either reals or complex or even finite finite fields like modulo what?
Just because maybe F can be the reals, or F can be the complex, or F can be the quaternions, no? or F can be whatever scalar field you like. For example, the scalar field functions in general. And then I think that this can be extended to any kind of geometry that you like for expressing the correspondingly for algebras in this kind of field. But I think that those are things that we need to work for expressing this in a correct way.
But this field here plays no role. The details of the field don't play any role in your development so far. So whether F is a complex field or not doesn't have any impact on what you're doing here, at least.
Yes, only this is important. I omitted this, but I think that I have to put this. And then in the Clifford algebra is expressed in terms of this F. And but only but not this is not changing this important relation. Okay.
Yes.
Yeah. Then okay. And now I'm going to speak here about more properties of the Clifford algebra. And then in the Clifford algebra, with this quadratic form defined, we have two morphisms of degree naught that are important. One of these is the product. The other one is the inclusion of the scalar field inside the algebra. Then these two homomorphisms are fundamental here, because with this we are building in this moment the structure of Clifford algebra. Then if we take these two homomorphisms, then we can build a monad that is used for build this Clifford algebra. You can see that we have the graded algebra category. We have here the tensor product, and we have here the scalar field.
Yeah, I think the finite fields are very interesting. That's where the Fano plane, Lunesto's last chapter of his book considers the Fano plane, and that's all related to where the field F is a finite field, or P to the n power, or finite define finite fields, which are, I don't know how they would fit into this discussion, but finite fields are very interesting in themselves, as Lunesto book points out with his idea of triality, and these ideas are pretty interesting too, but probably not quite related to what we're talking about now.
Yes, I don't know if it is we can relate, because I understand that the Fano plane is used for expressing the product in the properties of the product in the octonions. Then okay, octonions are a Clifford algebra, and then sure they have this property, but in the opposite direction, I don't know too much sure. Okay. Okay. And then we examine here the properties of the tensor product. And the properties of the tensor product then are expressed here in terms of the associativity of this tensor product. And with this, sorry, I think that part of the slide was lost here, because I wanted to speak here about the left and right unit, and he was lost here. In the paper are these properties, but not in the slide. Then I need to correct this, because it is important. The properties of the left and right unit that is used the scalar field. Okay. Then, okay, and then another property of the tensor product in the monad is that this is a bifunctor. Then this bifunctor takes to a Cartesian product of the of two categories. I think that I need to change here in these terms. For give a better presentation, I need to change this A by the lambda, capital lambda. Okay. And then if we see this property, and this is an important point, then we can build a covariant and a contravariant functor here that is wielded in terms of the home set of the category. Then with this, we can build the again the duality property in this category, that you can see here that the tensor product and the home set categories are duals. But we can extend this to the I lost. Okay, maybe first this, we can build here the dual space in using the building the home set between the module and the unit. Then in this case, for example, in terms of Clifford algebra, we need to put in this way, and then we have here this and if sorry, but I need here a module, then in this way. Okay, this expression is wielded here. Do you remember that we wielded with this the base of the dual of the space from the basis vector in this space. Then this is the expressed here in a categorical way. Okay. And then okay, then we go to the Clifford product. The Clifford products in these terms are wielded from these properties. Then we have here a quotient module that with the symmetric part of the tensor product. This is part of the Clifford product that is called the exterior is called the exterior product. Then here is the definition, and here we have the interior product that is wielded in terms of the antisymmetric part of the tensor algebra, like a quotient module of the tensor product. Here we have. Then with these two, we finally have the Clifford product defined here. But I want to go back here because with this definition, based in terms of the symmetric bilinear forms, we have that the contraction is the dual of the exterior product. Then we can see that with these two properties, finally we can work in this way. And maybe it is needed to add the graphic in this way. Here we have F, and here we have applying the exterior product. We have the different grades of the algebra. But we have here applying the contraction. This property.
That looks like local duality in a way, I think.
Yes, because you have here. Okay, if we can expand this figure here, if we have. Oh, sorry. If we have here I, and here we have I plus 1, then we have here this, and we have here this. And then these are the local duality in terms of subalgebras of the algebra.
Yeah, I think that looks very nice.
Okay. Then I think that this is the principal ideas here in this work. And I have arrived at the final slide, and then I think that now are the reference. Okay.
So in Dr. Sopcich's presentations, the notion of the scalar product or the dot product is not so central as it appears here, right? Not so. It's sort of more implicit, I suppose.
Yes, because if we have that the base of the algebra are are in these terms I no, sorry, because I need to put here the Clifford product. I am going to use the notation here. If we have this property, that is, if we are in the in an orthogonal space, then this product is equal to the then, but only the dot product is defined when we are in the orthogonal vector space. But this definition of the product that is a contraction is more general. And I think that it is important because this is the dual of the exterior product. Okay, I think I wanted to add another thing, but I have not enough time. But I think that it is important, and is how with this we build the observer ideas of Professor Rosiewicz. And then the question is how, if we have here a basis of, okay, I'm going to start with 0, 1, okay, I need to put in these terms. If we start with this base and we have the dual bases, how we can build a idempotent, no? And then remember that dual is the product without the element y. Then I wanted to build with the one idempotent with this element, and then I think that it is the tensor. Okay, the idea is that these two elements that I am going to use, that is I and 1 minus I, if we get the tensor product of this, we get the unit. How this is, give it to us E and E square, that is E. No, it gives to us 0. But, sorry, but the exterior the direct sum of this is the unit. Then both of these are idempotents, because E square is equal to E, and 1 minus E square is equal to 1 minus E. Then the idea of observer of Professor Osieri was that one I need to take, maybe it's the something is wrong here, because with this is the relation of observer, but I am getting here 0 for this product.
But E is idempotent?
Sorry?
E is idempotent?
Yes, E is idempotent. Yes.
Yes.
Yes. But if E is idempotent, then the product of these two are 0.
Yes, that is correct.
Because those are orthogonal. This is right. But here there is a problem, because how I yeah, sorry, because here I need the dual of one of these. Okay. In the wave, sorry, I am going to write this in another place because I need in this way the dual times and this is observer. Mm-hmm.
Okay.
This is the definition of observer, because in terms of the definition before, for example, if we use E not for representing, if we take now E not and the dual of E not is the product E1, E2, E minus 1. And then now the observer is this product sorry. Sorry, I have not enough space, but I'm going to write here observer is equal to E1, E2, En in tensor product with identity minus E not. Okay. Then I think that this idea is important because this is related with your idea, Professor Garrett, about the light ray. Light ray. Because an observer is related with this source.
Okay, I think it's, yeah, I think you're right. I think I can see it. Very interesting.
Why
Then,
do you use 1 minus E? Why?
Sorry?
Why is it 1 minus E?
1 minus E is not because is the complementary because where it because this
They're both idempotent.
we have two idempotents that the direct sum are the identity, the entire space.
Yes.
Mm-hmm.
But if we just write like E star tensor E, this isn't okay?
Okay, this is okay. No, because you say in this part?
Yes.
Yes.
Why not just E?
Because here we need the complementary part. In fact, I am taking this from this and this from this, but here is the dual. Do you remember that the definition of observer was, this is a differential form, and
Mhm.
this is a vector form.
Right.
And this is the dual. This is the dual of a differential form. But if we take the dual of this and this, then now I can write in these terms. Now I am using direct sum with this, and this is unit. Then and now I am inverting here the construction. This is I think that in the Young book of exterior forms, I think that this idea of building the entire space in terms of scalar forms, for example, and the dual of a vector forms, we can describe the entire space. But I think that this is clear, this expression. Because I have performed here a partition of the space. First, we built a partition of the space, and then with this partition, we built the observer.
Yeah. Okay, so can you say about that partition tau and t? That's equal to the observer.
Yes. Mm-hmm.
Mm-hmm.
I just think it's interesting that the complement is an important part of this. It's not obvious in what Oshevich was doing, that the complement enters in this way.
Yes, but I think that it was implicit in the ideas of Eric.
Mm-hmm. Yeah. So every observer corresponds to an idempotent, then basically.
Mm-hmm.
But all of this is generated by E, but you need both its dual and its complement
for the observer. For building the observer, I need the dual and its complement. Yes. Mm-hmm.
Yeah. The other idea is an observer corresponds to a Dirac light-like vector, gamma squared equal to 1. Every observer in the Dirac algebra, gamma squared 0 is equal to gamma 0 squared is equal to 1, and that corresponds to observer. But that's a different way. You can, of course, define an idempotent tau with that by 1 plus gamma 0, then 1/2 of. So I think these ideas are all closely related, of course. Regarding an observer is also in the Dirac algebra, that's gamma 0 corresponds to, each observer corresponds to a unique unit vector, gamma 0, in the Dirac algebra.
Yeah.
But is it necessary to have the Dirac algebra only so that you can have this complement? So I'm still a little bit struggling with the relationship of the quadratic form, like why in conventional like definition of Clifford algebra, and in, for example, the Dirac algebra, whatever you're dealing over a quadratic form with a particular signature. But here we don't. This is not concerned with signature at all. But it is important that we have this complementarity, or that the idempotents, we need an algebra in which there are idempotents of this type, right?
Yes, but I think that the signatures are inside the quadratic form. Then here we cannot define it explicitly, the quadratic form. But if we define explicitly the quadratic form, then we can speak about the signature without, I think, without problem.
That's right. Each observer corresponds to a decomposition in your category theory. I think it's just, yeah, a metric really, it's overly emphasized. I believe the quadratic form is, in a certain sense, is superfluous, or not necessary, really, because every observer corresponds to a different Minkowski space-time of that observer, or the polyalgebra of the even subalgebra of the Dirac algebra is the polyalgebra, and that's a decomposition that I think that we're getting at in terms of category theory right here. It corresponds to a decomposition in category theory, where your objects now in this case are Clifford algebras of Minkowski signature.
Okay.
It seems like a good topic for next time. This notion of complementary idempotent, and
well, I think we are making progress, actually. I think it's been very useful today. I think Dr. Cruz has done a great deal of work understanding how all these ideas fit together. I believe that he's showing that they do fit together. Although I had some doubts at first, but I believe that this is good, very good.
Okay, thanks.
all right. Did you want to make any comments, Dr. Sopik, about the email that you sent?
Well, maybe even in light of what you've done, what Dr. Cruz has done today, it can be made much better. I mean, of course, I'm interested to see. He's going to try, I understand it, incorporate some of this, but I think we can probably do it much better. Maybe, do we still have another through? When is this conference, the conference that you're going to, Dr. Cruz?
Is the next week.
Next week? Okay.
Next week, and in fact, I present next Monday.
Oh, okay. And where is the conference at? It's in Turkey?
No,
Croatia.
now Croatia.
Okay.
Do you have an opportunity to travel in Croatia when you're there?
Not before, but maybe I have not too much time for traveling inside Croatia, but we are going to fly to Budapest Hungarian.
Ah,
Mhm. And then we travel by train to Osijek. Osijek is the name of the city in Croatia. Mhm.
that should be a very interesting trip by train.
Yes, I think. I think.
Yes.
Mhm. Okay.
If you do get an opportunity to travel in Croatia, I suggest to go to the coast to a city called Split.
But it is too much far from the Osijek city because
Yes, I think it's
Osijek
quite.
is in east of Croatia. Mhm. This part.
Yes.
Mhm. Then when the organizers proposed Croatia for this meeting, they was thinking about a place in the sea. But after they changed, I think because for the organization was better because this is inside of the University of Croatia. Then I think that there are better installations for this.
I see.
Mhm.
I hope you have a very good trip.
And thanks a lot.
Yeah, it's very
And,
exciting, actually.
Okay, so I think that's a very good presentation for today. We look forward to hearing about your trip and in 3 weeks.
So you'll write a paper after this. When do you have to turn in the paper for the conference?
The paper to the conference was sent for the proceedings of the conference.
Oh,
But
that's already done then.
maybe we can make short corrections. We are in time, but not too much change. But after we can publish some extended version inside the inside a journal, for example, that they are publishing, or maybe in another place. But I think that now we have good material for another kind of publication.
I would be very interested, of course, if Dr. Ojevich could see this material.
Yes.
Yes, indeed.
Mm-hmm.
Okay.
Okay.
Well, look forward to seeing you both again in 3 weeks' time.
Okay. Okay.
Bye for now.
All right.
Bye.
Take care. Have a safe trip.
Thanks.